this equation here. So suppose we want to go about looking for a steady state distribution for the Vaz-Check model. We know that this is what the Vaz-Check model looks like. This bit here, that's A. This bit there is B. So you substitute this into the relevant parts. So the B goes in here, and the A bit goes in there. And in the case of the Vaz-Check, this is what we end up with. The nice thing about this is that this is actually a relatively easy differential equation to solve, because integrating both sides means that the very first derivative will become a first order derivative. So if we were to integrate, the first term becomes a first order derivative, and the second one no longer becomes stays a derivative, and then what we're left with is a first order differential equation. So this is, I mean, is it something that you wouldn't mind trying as an exercise, or do you want to see how it works? This is the solution. What are your thoughts? Maybe I'll start you off, or are you noisily confident with this one? Something for light bedtime reading. Let's make a start. Right. Can you just tell me what the equation was?
Half d squared.
Half?
D squared by dy prime squared.
Wasn't it an r?
No. Y prime squared.
Yeah, there was an r in there. Yeah, thank you, that's the one I want. Yeah, I won't have to then keep, that's it. Half sigma squared, r squared. Let's forget the primes, all right? We don't bother about the primes. And let's drop the infinity notation also. The reason being, gamma d by dr, r bar minus r p. Right, there we go. Thanks. That's the equation. Why don't I pull the minus out also? So I change this to r minus r bar. There we go. Here's the equation. There we go. Integrate both sides. So if we integrate both sides, integrate, oh dear, oh dear. Integrate throughout. The left-hand side becomes a half sigma squared. dp by dr is equal to minus gamma r minus r bar p plus a constant c. C is equal to 0 because out in the tails we have p tends to 0, and so does dp by dr tend to 0. So therefore the constant of integration is gone. What do we have next? Well, we have a nice, if I take the thing on the other side, so dp by dr, let's write this as minus 2 gamma over sigma squared. Then we've got an r minus r bar p. That's the resulting equation. Right, 2's gone across, and I divide by sigma, and that's what we got. Right. Now, that's also a nice differential equation. It's first order variable separable. So we take all the r's on one side, all the p's on the other side. What we end up with, I'm going to forget this last line on the next page. So let's get rid of this. And what we have here is, what was it? It was dp. So let's take this on the other side. And then on this side, I think it was minus 2 gamma over sigma squared, r minus r bar dr. There we go. And we integrate both sides. Now, the term on the right-hand side, we could integrate that, but then would have to do some completing the square on the exponent. What we can do instead is the following. If we note the following, this will mean we won't have to do any integration at all. because if I was to write down, r minus r bar, and I squared it, and I differentiated it, and then I divided it by 2, would you agree that that integrand there is the same as the integrand above? The same thing, isn't it? Which means if I bring that 2 outside, that goes, and then we don't actually have to do any integration. Everything's been presented to us on a plate. This then becomes r minus r bar squared, with a minus gamma over sigma squared. This is log p, and then p becomes the exponential of all of this. But then there's a constant of integration there, so that comes out minus gamma over sigma squared, r minus r bar squared. And this is a PDF, so if we now integrate between minus infinity and plus infinity, use the fact that the integral of e to the minus x squared is root pi, like last week, you'll then get the answer on that slide. All right, so the only thing you need to now do is do the last step of working out what the a is. And that's all done. I'll put the full working in the extra notes for this session, so you'll see exactly what's done. So that was something on the steady state distribution. The last thing, just before we go on, is the backward equation looks like this. Remember last week we also talked about the backward equation. There's an equivalent backward equation for a stochastic differential equation. This is what it looks like. Again, you can see there's an extra term in there because of the drift. This is actually important for one reason. The Black-Scholes equation is a backward equation, but more on this later on. That's part 2 done. Now we come to part 3, which is simulating stochastic differential equations. The stochastic differential equations that we're looking at are continuous time processes, and we need some way of discretizing them. When it comes to notation, what you need to appreciate is when you see d's, that's continuous time. If I was to write this in, so this is continuous time. If I decided to write this in discrete time, I'd use deltas instead. And then over here, phi times root delta t. So this is now discrete time. We also know that delta s is si plus 1 minus si. So if we replace that, and I take the minus si to the other side and factorize, what we then end up with is a time-stepping scheme. So if I just come down to the next slide, this. Have a look at this. This is intuitive, isn't it? This is telling us that if we're at time step I, we know the stock price, we can use this formula to work out the stock price at the next time step. Agreed? So we will start this at I equals 0. I equals 0 would be your stock price right now, the one that's appearing on the screen. You want to know the stock price at the next time step. It could be the next day or next month. You choose what delta t should be. That is called the Euler method, and it has accuracy, which is order root delta t. So this is a numerical scheme. The name given to it is actually, it's Euler Maruyama method for simulating stochastic differential equations. This is assuming that we know what SI is. We know the stock price at this time. Let's assume that we know what mu is. We also know what sigma is. Delta t could be daily stock prices. So delta t is 1 over 252. And then we start number crunching. And this is what we're going to use. So if you make a note of this, that we're going to be using this shortly when we come to doing our simulations on the Excel spreadsheet. Okay? So if we come down here, so what this is basically doing is what we just said. This is simply defining everything and how we'd use it. Now, what about generating random numbers? The thing that we're interested in Excel is how to go about simulating this, N01. And you could do this using the function norms inverse rand. Who's used norms inverse rand in Excel before? Do you know anything about what it is? I.e., norms inverse rand, what does it represent statistically?
So, wouldn't that be the density function? Wouldn't it be that?
So rand picks a normal number between 0 and 1, which will be the probability that we plug into this.
Right.
And because it's an inverse of an old distribution, we plug in the probability and we get the value.
Yes, so good. So norms inverse mathematically is which function?
Inverse of the CDF. Inverse of the CDF.
Yes, it's the inverse of the cumulative distribution function. We know that n of x is this. It also represents the probability that a random variable, an observed random variable, little x, lies to the left of big X. That's what it's saying. So it's somehow flipping that over. So as our friend said, we pass through a probability because rand 0, 1, a number between over 0 and 1, is the probability. And interestingly, n, which is uniformly distributed, n has its own distribution. That's the interesting thing. Diagrammatically, it's this. Here's n of x, here's x. If you flip this over, what you then end up with is along here, you've got rand, and along here, you've got your n01. That's what the inverse cumulative distribution function is doing. Right? So you pass through u01, which is what rand is, and in return, it'll give you an n01 number. The reason why it's slow is because inverting an integral is slow business. So this is one way. I'm going to use that. Paul will always use some other method, but I prefer that. The other way to do this is a faster way, but it's inaccurate. The smallest amounts of rands you can use and get away with is 12. So sum up 12, subtract off 6, and this is a crude approximation to n01. That's where that comes from. And I think on the next slide, Paul says y12. You want to make sure that you get a mean of 0 and a variance of 1, or standard deviation of 1. So this will work. Why don't we do something slightly neater? Why don't we derive the general result for that? That's a special case. We know that rand, rand is u01. That means it has a mean of a half and a variance of a 12th. Those are the statistical properties of u01. Let's sum up a whole load of these. So if I sum up rand, I goes from 1 to little n. Let's sum this up. We work out the expected value of that, in other words, the mean. Sum of expected value of rand, I goes from 1 to n, so therefore we've got n times a half. So not quite the 0 that we were hoping for. So that tells us that we can update our formula by subtracting off n over 2, because at least we're guaranteed a mean of 0. What about the variance? Let's test the variance of this. We don't need to worry about n over 2 because we know that the variance of a scalar is 0. So if I then take this inside, and we've got n lots of 1/12. Not quite the one that we were hoping for. So that tells us that perhaps we need a normalizing constant. We multiply that expression with something so that we get a value of 1. So let's say alpha times all of this stuff. And that should all equal 1. Right, let's pull the alpha out. So alpha squared. I'm just trying to finish this on the same page. I don't think it's going to happen though. We know that this thing is n over 12. Agreed? So in order to finish this on the same slide, so I know exactly what's happening, we've got alpha squared must equal 12 over n, therefore alpha is that. That is now the full formula, of which if you put n equals 12 in there, that'll collapse down to the one that Paul's got on his slide. This simply means that as we increase the number of n, the quality of our n01 will improve. Right, so that's the other way of doing it. Right, inverse, okay, Brian, thank you. Again, I'm sorry, what is the phi here in the Euler equation? No, in the Euler, you don't mean the Euler equation, you mean the Kolmogorov equation. The phi there refers to a probability in that particular case. Phi plus the probability of the random walker going up, phi minus the probability of the random walker going down. Okay, so that's the full thing. So if I just come down here and I write it down in this way, 12 over n times the sum of all of these rands minus n over 2, I goes from 1 to n. If I rewrite this, so it's the sum of all of these rands minus n times a half. Let me take the stuff outside downstairs. So I get root n times 1 over root 12, like that. All I've done is I've rewritten that formula in that way. Let's compare it to this. yi here, yi is independent and identically distributed random numbers. I goes from 1 to n times n times mu over sigma times root n. So you can see our formula is consistent with the central limit theorem. And that's the reason why it works. That's the reason why this will give us an n01. Right, so what we've done is we actually derived our own formula. Okay. That said, I'm still going to use Norma's inverse rand when we do the number crunching. Now, we need to move along. Right, so everyone happy with this? This is the kind of thing we're going to do in a moment. Simulating other random walks. Here is Vasicek. So you can use this Euler method to simulate any random walk or stochastic differential equation. So dr is ri plus 1 minus ri equals all of that. What we're going to do is we're going to simulate it in this form. So ri plus 1 is equal to ri. Then we're going to have a plus eta minus gamma ri delta t plus root beta times phi root delta t. That's going to be, make a note of that, we're going to use that shortly. Okay. That's Vasicek. in discrete form. Masicek in discrete form. Okay. Now, the one thing, one of the things you can do, you want to get the, if you want an insight into the dynamics of any stochastic differential equation or the dynamics of an asset price, you can do it by switching the randomness off. It does actually tell you quite a lot about what's happening. Put root beta in Masicek equal to 0. Why? That means we're switching the randomness off. What we're left with is this. Agreed? Sorry? Yes, deterministic. Yeah, the fact that we switch the randomness off means that what we're left with is something deterministic. Let's solve this. Ordinary differential equation is equal to, what was in the previous? Let's have a look. Minus gamma. There we go. Questions. Can you define alpha? The alpha. Which alpha was that? Did I use an alpha a little while ago? Alpha is a normalizing constant. Minus gamma dt. Integrating r minus r bar log is minus gamma t plus a constant c. R is equal to r bar plus a, whoops, let's get rid of this. That should be a plus. Where's the pen gone? There we go. Plus a e to the minus gamma t. That's actually very helpful. In fact, it's very insightful. That's telling us that the role of the gamma is actually exponential decay. When gamma is large, a e to the minus gamma t will vanish very, very quickly. When gamma is small, it'll take a long time. And what r will tend to is r bar. So we do a diagram. Based on that e to the minus gamma t, we've got the following. There's r bar. Here's gamma high. Here's gamma low. And what's going to happen then change the color. When gamma is high, if the spot rate or the interest rate is above the mean rate, it'll tend to the mean rate like this. If it's below it, it'll do this. That's when gamma is high, because exponential decay is pretty rapid. If gamma is low, it'll be a lot more gradual. It'll do something like this. So even by looking at half the problem, by switching the randomness off and looking at what the drift is doing, remember the mean reversion comes in via the drift. It gives you a good idea of what's happening. Right. What have we got left? There's a simulation of something with extremely high gamma. Look at that. I can't remember what. Very odd looking though. Very high gamma. Very high gamma. Right, the last thing we do before we do our laptop bit is producing correlated random numbers. Why do we need that? Suppose you're pricing derivatives. It's highly unlikely that you'll price a derivative on just one underlying. When you price derivatives, you have to know what the underlying is doing. Suppose you need to simulate two random walks. You've got two stocks. Each stock has its own mean of returns and standard deviation. How do you correlate them? It's all very well producing random numbers, but we need some way of correlating the random numbers that we've got.